Today we're going to look at adding vectors using components. And what that means is we're going to break them down. So you're going to break down into x and y components. That's what it means. So the first step here is drawing these correctly. This vector is at an angle which is north and then 35 degrees east. So this would be north. That's how you would orient yourself at the beginning. And then you would rotate around 35 degrees this way. So we're going like that. And here is our vector, 125 meters. So we started off north and then we rotated 35 degrees to the east. So there's your north, there's your east, and this is going to be dy, this is going to be dx, and we're going to break that 125 down into the horizontal and vertical components. Well, let's put the other one over here and give ourselves lots of space. This one says orient yourself east, which is this way, and then rotate 64 degrees to the south. So that's going to take us like this. So we have oriented ourselves east and then rotated, right? So there's your east. We've rotated in the southerly direction 64 degrees. So again, this to me is the most problematic part. Once you've got this done, the rest of it is pretty mechanical. So we've oriented from north towards the east, and here we've oriented from east towards the south. So now all I have to do, and again, this is your dx, and this is your dy. And so let's look at these separately. In this one here, the dx is going to be 125 sine 35 degrees. Why sine? Because the sine, or the vector, the component here, is not touching the 35. And the way it goes is this. Touching gets the cosine, not touching gets the sine. And it works like that every time. And then the dy is going to be 125 cosine 35. So if I were using this angle, I would switch the sine and cosine. So let's see what these components are. 125 sine 35, 71.7. So that's 71.7 meters, and this is to the east. So I'm just going to call it positive. It's just going to make things easier here. And then the y component is going to be 125 cos 35, which is 102 meters. So we have 102 meters on this side, and we have 71.7 meters on this side. And that looks about right, the way that I've got it drawn, 102, 71.7. It looks like it conforms pretty well. Now over here for this one, your dx this is going to be the cosine one. That's 75 meters. So it's going to be 75 times the cosine of 64. And the dy is going to be 75 times the sine of 64. And 75 cos 64 is 32.9. And 75 sine 64 is 67.4. So on the x-axis, it would be 32.9. And on the y-axis, it will be 67.4 meters. And I don't really have this drawn to scale. That 64 should be like more down here. Unfortunately, I didn't draw it quite right. But these are the measurements that we get. And because this is going down, right, or to the south, I'm going to call this negative. So instead of writing down north and south, I'm going to have like positive, negative, but the two east ones are both positive. So now I have the the dx overall is going to be 71.7 meters to the in the positive direction plus 32.9 meters. So that's our total x displacement, 71.7 plus 32.9. And we get 104.6, and I can leave that 0.6 in there because we're adding, and it's one place past the decimal. And the dy in this case is going to be 102. That's in the positive direction. And then we're going to subtract 67.4 because it's in the opposite direction. So 102 minus 67.4, and that's going to give us 34.6. And I'm going to assume that's 102.0. So that's going to be 34.6 meters, and that's in the positive direction. That allows us now to construct a new right angle triangle. And the new right angle triangle is going to have an x component of 104.6 meters to the east. And then the y component is going to be a positive 34.6, right, in the northerly direction. And let's get a different color here. And so the overall displacement is this. So we've broken down each one of these two vectors into their x and y components and added the x components of the two vectors and added the y components of the two vectors, and we end up with this new triangle, which we can now use the Pythagorean theorem on and our trig function. So now we can get the resultant. It's going to be the square root of 34.6 squared plus 104.6 squared, which is 110 meters. And the theta is going to be 10 to the negative 1 of opposite, which is 34.6, over adjacent, which is 104.6. So it's going to be shift tan. On my calculator, it says shift tan, 34.6 divided by 104.6, and I get 18.3 degrees. It's a pretty low angle, but that looks about right. 18.3 degrees. And then to properly write this vector down in proper notation, the resultant vector, that's what the R stands for here, is a resultant displacement. It's going to be 110 meters, and then we would orient ourselves east. You would point yourself east first, and then you're going to rotate 18.3 degrees in the northern direction. So that is the overall displacement from those two vectors. If you look at that movement and that movement, we end up here, 18.3 degrees north of the eastern orientation, 110 meters. And that's a lot of work, but that's how it's done. I mean, really, what would be nice is if you had a computer program and you put in the vectors with their lengths and with their orientations, and the computer program would be there would be code written to break it down into the x coordinates and then add the x coordinates together and to do the same thing with the y coordinates. And you could write a little computer program that would go through this entire procedure, and you could put in as many vectors as you like, and it would give you an overall resultant instead of having to do all of this number crunching by hand.